Thank you very much for having me here in Ray Summit. Very excited to be here and talk about software 2.0 and what it needs. And here we're going to introduce about data 2.0 and how we are thinking about storing and managing unstructured data sets for deep learning at Activeloop. Before starting the main meat of the conversation, I'd love to get into details what I was doing before. I was doing a PhD at Princeton University where I was in a neuroscience lab advised by Sebastian Seung. And the problem that we were working on, we were taking a mouse brain, cutting into very thin slices, imaging each slice, and then applying machine learning and deep learning at scale to transform those images into segmented neurons and then find the connections to build the connectome or the graph of the connections. Each slice image size was 100,000 by 100,000 pixels, and we had 20,000 of those slices as well, so it was around a petabyte-scale dataset. And if you apply a deep learning pipeline on petabyte-scale dataset on AWS, it becomes very expensive. And our goal was to reduce this cost to 200 or like 2 or 3 times cheaper by rethinking how the data should be stored, how it should be streamed from the object storage to the computing machines. Should we use CPUs and GPUs? What kind of models to use? And how to scale all this processing on like 100 or 1,000 machines on the cloud at the same time. That's how we got into Y Combinator, then raised our seed fund, and we have been working with early customers to help them to be more efficient in terms of large-scale machine learning applications. One of the customers we worked with was in legal tech space. They had 80 million text documents, and their problem was to train an embedding model to be able to very efficiently search the data. And they were spending like 2 months to train a single model on GPU. And we also worked with another architect company that had airplanes flying over the fields in Illinois. They were collecting unstructured data sets of aerial images of agricultural fields. And the problem was to provide insights to the farmers where there is a disease in the field or dry down area. And we cooperated with Intellinear to help them to plug the unstructured data sets to the machine learning models. They can train a lot of deep learning models to do crop classification or identifying segmenting the pixels for dry down areas and so on to provide us insights. And what we learned so far is that the problem is actually not in the training or the deployment of those models. It's actually in the data, how people store unstructured data sets. We use a lot of files, images, etc. And it's a lot of time consuming essentially, even today, to process this data and extract valuable insights for the businesses. It's still data scientists spend 80% of their time on preparing data. And what we try to look for is like, even if you try to go and Google search, like, can you give me a database for images? What you find out is that all these tools, like they all suggest like still store all your data in a MySQL or a tabular database and have additional column that points to the files. But if you want to do a machine learning on top, it's pretty inefficient. And there's no any database, data warehouse, data lake for especially specialized for unstructured data so that it's very efficient to do machine learning on top. And that's what we decided to focus on. So what we are working on is essentially building an industry standard for storing unstructured data sets and then streaming them to software 2.0 or machine learning purposes. And here what we did, introduce basically a new standard for storing and streaming those data sets. You can think of it as like serverless NumPy arrays. Those are like, you can store the data and stream the data in unified arrays on the cloud. It can scale to any machine and at any scale and be accessible for each of those machines as if the data was local to the machine. I'll get into details, what does it mean literally, but this is what we do. So let's say you have a million images, they are sitting on your file system or they are sitting on an object storage, and you want to be able to very efficiently stream them to machine learning frameworks and train a model, and you do have to do all this heavy lifting of taking this data, writing like hundreds of lines of code, boilerplate code to read this, and then plug this into TensorFlow or PyTorch just to start training a single model. But what if you want to do distributed training, or what if you want to do like run a lot of different versions of the data set and be able to do? And what we do is that we take all your different images, transform them into tensors, and then very efficiently store this on your specified cloud location, could be on S3 or Google Cloud, such that when you stream the data from that location, it becomes very inefficient to take this data set to stream to the GPU. And for the GPU, the data is actually feels the same. The throughput that we can achieve, maximum throughput, there's not any much difference. So if we get into the machine learning life cycle, we have this collection, you annotate the data, and then the data scientist or machine learning engineer, they spend a lot of time on data wrangling. And then they have to train this again. Of course, once you start doing it, build your first data pipelines, and it becomes much less time, and then you start tweaking it and so on. But for every use case, you have to spend a week or 2 weeks just to set up the whole data pipeline to train your model. And with Activeloop and Hub, and we are like taking this chunk of code and then saying that, hey, instead, machine learning engineers, data scientists, they can actually focus on the most important part of extracting value or insights from the data itself, instead of doing this data janitorial work of, hey, we should set up the pipelines and so on. And what we did with Waymo, we did a collaboration. Basically, they had a data set, 2 terabytes, has 1,000 TF record files, each of them like kind of combined into zip files stored on Google Cloud storage location. And for an average data scientist, it spends like at least 2 days just to download the data, unzip those files, understand their API, find all the data, and then access a particular slice of the data in average. And what we did for them is that we transformed their data into our format and store it back on their Google Cloud storage so they have the full control. And data scientists now can, with just single pip install Hub, they can literally access the data and start working with it while it's getting streamed to their machine. And there's no any need for having all these different layouts of the data with compression and TF records files, and then in TF records files you have protobuf files, you have then you have the each like image in JPEG format laid down in bytes and so on. So we simplify all this. More specifically, we focus on those problems where you see that, like, essentially when you're trying to train or deploy a machine learning model, or you want to do a compute, you want to make sure that the data is local. So you want to make sure that you don't spend a lot of time on transferring data from one location to another location. You want to make sure that you own the local folder structure dependency. Let's say you train a ImageNet on your local file system, and then you want to train it on larger scale. You have to copy all the same kind of structures. Otherwise, you have to change the code. So you want to be able easily, without changing any line of code in the way you read the data, to be able to scale to a cluster. And we'll get into details like how you can do it actually with Ray at any scale. And then another question very, very relevant to this topic as well is building these pre-processing pipelines, where you have to take care of, okay, you have a data set, you have to apply a lot of transformations. What is the best way to write those transformations, keep track of them, version control, and then plug this into machine learning algorithms. If you're working with a team, you have to make sure that the data is accessible to your team members, and they can easily plug into or combine their data sets together to train a model. Let's say you just want to access a specific data set, and then, or a part of the data set itself. You don't want to unzip all the files, or you don't want to just read linearly all TF record files just to get the piece of it. And of course, there's like the issues with in-memory management and visualization. We do also provide a visualization tool that helps you to instantly see the data, and the 2.0 visualization is soon coming. That's gonna have mind-blowing visualization. Here you can see that you can easily see all the data in the image formats that we do provide. And more importantly, from the developer perspective, there's no any need for writing these 4 lines of code. Just reading here Fashion MNIST dataset. Like Fashion MNIST is like a very small, like 50 megabyte dataset, and you have to write all this boilerplate code just to get the images and labels to stream to the training process. And we want to automate this whole part where data scientists don't write. More than that, besides just simplicity or easy of use, we also focus on the performance. We did compare us with the TensorFlow datasets plus Ignite server. So what TensorFlow datasets does is like it's a way to load the datasets. Then you have an Ignite which keeps the dataset in memory in a cluster. So they tried to run the full line 2 benchmarks where they have Ignite running on a same machine in memory, and then you can achieve like 875 megabytes per second to TensorFlow to the GPU. And what you can do else, you can take the Ignite and then put it on a remote cluster where the machine doesn't own the dataset internally, but it can stream over the network to the GPU to train, and you achieve 800 megabytes. With Hub, and what we can achieve is that we can achieve 875 megabyte per second network utilization to the GPU as if the data was local to the machine, but without any in-memory database and with 20 times cheaper cost, as you would expect, because there's no any data in memory stored. And you can actually scale this to multiple machines at the same time and then stream this data to each of those machines just to train, deploy, or maybe run some query on top of them. And here you go. Most importantly, what we are excited to share is that we also did an integration with Ray. What you are able to do, you're not only able to store your datasets locally, but and as if it's stored locally, but you can also essentially take a transformation or piece of custom arbitrary code you want to apply and then scale this to a cluster. So Ray does a very good job in taking a custom lambda functions, or could be like transformations written in Hub for Hub. Essentially, we take that, translate it into our format. The way we store the data is very efficient to run the computations, and then we scale it to the cluster, run the computation, and bring back another data set. And you can do this with very high utilization of both CPUs and GPUs. And we did a benchmarking as well, just to compare the benefits of having Ray plus Hub versus Beam. Apache Beam, we had a use case where one of our customers had a single job running on Apache Beam in Dataflow to have been spending like 500 CPU hours to process a dataset, transform a dataset into a TensorFlow datasets, and end up actually, the dataset itself ended up with low GPU usage, and the cost per round was around $29 per it. The amount of the data was getting, I think, around 3 terabytes. What we did with them is that we took Hub, we took Ray as well. We write a connector to their dataset originally, and then scale this to a cluster of AWS machines. And what we achieved is like around 5 times better performance and better cost as well. And doing the same amount of job with 100 CPU hours, and like the dataset that's ended up being output of this machine can have been like very highly utilized with the GPU to train the model because of the format and the layout over there. I'm very excited about this like kind of partnership here. And this technology itself can be used for a lot of use cases that we have seen so far. We have worked with our partners in Telenair. They have this petabyte-scale datasets. We work with a legal tech company. We also work with another customer of ours that help them to optimize the data processing for their team of 50 data scientists working together. And we also seen our open source tool growing and building a computer vision basically, and not only a community where we would love to welcome anyone to join us and help us building Data 2.0, which is a new way for storing unstructured data sets and then streaming this to machine learning platforms, and very well integrated with Ray to run all those computations at scale. We essentially, just a couple notes that what I would love to give a takeaway with you. It really takes a lot of time to connect to unstructured data and train machine learning models. There's not actually widely adopted tools for storing and processing unstructured data. You have a lot of databases, data warehouses, data lakes. They're not very well suited for deep learning applications. And with Data 2.0, we want to structure all your unstructured data sets in a very simple and unified way. So love to, if you can just run pip install Hub or switch to Data 2.0 and join our community as well. Let me know if you have any questions. Feel free to reach me out over the same email, or you also have my personal email and Twitter account. Feel free to contact us at any point, and we'll love to get into details and see where we can be helpful.